This lesson is 5-6, Historical and Exponential Depreciation. Example 1. Determine an exponential depreciation equation that models the data in the table. So just like in the last lesson where we did a linear regression, this time we're going to do an exponential regression. Okay? So an equation, the same word is regression. Okay, so we're going to do an exponential regression. All right, so grab your calculator and let's get started. So again, we're going to go home, start new, do a list in a spreadsheet, go up and call this X, hit tab and call that Y because we have age and value. So go and put the ages in and the values in. When you're done, continue the video. So the difference here is when we do menu, statistics, stat calculations, instead of one variable stats or linear regression, we're going to go all the way down to A, exponential regression. Everything else is the same. So you have to tell us what your X list was called and what your Y list was called, and then OK. So notice I'm in the middle of my table again, so I want to go up. There's my equation, so please make sure you write down your equation. So y equals a, I don't have to put the star for times, I'm just going to put b in parentheses and it's raised to the x. Then I am going to go down and notice here you can see your decimals. And I caught a mistake, I had 80 here instead of 70. So the thing you want to be careful of is see how they round that to a 9, but when you're on the box, down here you can see the whole decimal. So be very careful. So we're going to round to the nearest hundredths. So on my paper, I wrote the equation y equals a times b to the x, and now I'm going to write the actual equation. So a is 25,921.87 times b, which is 0.92. And that's raised to the x. So this is what you want to have on your paper. Okay, we wrote exponential regression, so we know how you got it. This is the standard equation for an exponential regression, and this is the equation. So now, if we go back to our calculators and we go home, don't do a new document because that'll get rid of it. If we go down to this pink box, we can see the scatter plot. And you're going to hit the bottom to click to add a variable, so add x, and then go over and add y. And I love when you can see the dots dance. And from here we can also write the exponential regression, but right now you can see that this scatter plot looks like the one on your paper, similar to it. And you can see that this is in the shape of an exponential. So if you weren't aware of the shape of an exponential, you now know what it is. So we can also write it from here, the exponential regression if you want. So menu, analyze, regression, and there it, sorry, I hit the wrong one. So menu, analyze, regression, and I want exponential, so number 8. And you'll see that that is similar to what we have, not rounded correctly. So again, if I wanted to change, I would do menu, settings, and I want the digits to float. And you can see how they change. And I'm just grabbing this and moving it. So I'm using my click pad. All right. All right. So the question at the bottom is, how might a better fitting exponential depreciation look when superimposed over the scatter plot? So superimposed just means on top of it. So it would be closer to the dots. So you can see in our calculator one here, see how this regression equation, this exponential, doesn't hit the middle of every single dot, and it almost misses these two. So it would be closer to the data points. So if it was perfect, it would be right through the middle of each dot. So it would be closer to, I'm going to say center of data points. All right. So, all right. So on the next page, we have to write our two exponential decay equations. Do you remember them from if you took Algebra 2 or Trig? So y equals a 1 minus r to the t. Or you could have y equals a times b to the x. And remember that if it's decay, b is going to be less than 1 but greater than 0. So it's going to be a decimal or a fraction between 0 and 1. Okay? All right, so go ahead, pause, and read example 2. So in example 1, our base, or our b value, is 0.92. It is between 0 and 1. So if we want to find the actual rate, the depreciation percentage, we're going to set it equal to what's inside here. So we're going to say 1 minus r is 0.92, and we're going to find that rate of depreciation. So r is your rate of depreciation, and it is a percent. So how do we solve for r? We subtract 1, so we get negative r equals negative 0.08, divide by negative 1, so r equals 0.08. How do you convert a decimal to a percent? You multiply by 100 or move the decimal over 2. So this is an 8% depreciation. Okay? All right, so why don't you try the next one? So writing the equation should have been easy. Now again, because that thing in parentheses, that base, is less than 1 but greater than 0, we know that 0.88 equals 1 minus r. So we're going to subtract 1. So we get negative 0.12 equals negative r. Divide by negative 1. Notice it's exactly the same steps as above. So we have 0.12 equals my r. So now I'm going to multiply by 100. So my rate is 12%. So I am losing 12% a year. Hopefully my time is in years, okay? All right, so example 3. Iman purchased a 4-year-old car for $16,400. When the car is new, it sold for $23,000. Find the depreciation rate to the nearest tenth of a percent. So to find the rate, we have to find the base. So the base is the current value over the original value. So the current value is 16,400, and the original price is 23,000, and we're going to raise it to 1 over the time. Well, that is 4. So go ahead, me being off the screen today, holy cow, and plug that into your calculator. So you should get a decimal of 0.9189 blah blah blah, and that is your base. So again, just like the other questions, your base, since we're trying to find the rate, we have to do that this base, 0.9189 blah blah blah, equals 1 minus r. So we have to subtract 1, and again, I'm just using my calculator, so minus 1, so I get 0.08107 blah 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 equals negative r. I'm going to divide by negative 1. So 0.08107 blah 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 equals my r. So now I'm going to multiply that by 100 to make it into a percent. So I get 8.1 because it says the nearest tenth percent. So this is decreasing or losing 8.1% a year. depreciating. That's what depreciating means. So this check for understanding is a little bit different. So a car originally sells for $30,000. After 2 years, the value of the car has dropped exponentially to $25,000. Find the exponential depreciation rate expressed to a nearest percent of 100. To the nearest hundredth. So I lied. This is exactly like the other one. So pause the video and you try. So hopefully you got a rate of 8.71%. So I used the formula from the previous page and got 0.91287 ... and then I set it equal to my 1 minus r. Example 4. It's a little bit more difficult. A car originally sold for $26,600. It depreciates exponentially at a rate of 5.5% per year. When purchasing the car, Richard put $6,000 down and pays $400 per month to pay off the balance. After how many years will his car value equal the amount he paid to date for the car? So we have two different things going on here. We have an exponential and a linear. So the exponential is the sold amount, and it depreciates at a rate of 5.5% per year. So we're going to use our equation from the previous page. So not y equals, we're going to use d because that's the depreciation amount. So d of x equals a is the original amount times 1 minus 5.5% raised to the x. Then we have the amount we are paying, so our expense. So our expense is 4,800x. Well, how do we get 4,800? Well, the problem is this is per month, and our time is per year. So I took 400 and I multiplied it by 12. So in a year, we pay $4,800 for this car times years plus the $6,000 originally as the down payment. So now we need to graph this. So go ahead and grab your calculator. And once you have them graphed, we don't see anything. So it's hard for me to get on that 6.67. So I'm going to go on the -10 and I'm going to hit tab twice. That brings me up to the 6.67. My y-intercepts, my original value was 26,600. So I'm going to call this 30,000. I'm going to hit tab and I can see my intersection. So I'm going to hit enter. So I'm going to show you another way to find the intersection. I know we used geometry in the last lesson. Let's try it a different way this time, and you can choose which one you like better. So menu, analyze graph, intersection. Click on one side of the intersection, it doesn't matter where, and then swipe across and click on the other side. Your intersection has to be in that shaded area. So now we have to graph this onto our paper. So pause a minute and get that sketched on there. I'm only going to do quadrant 1. I'm not going to do this area in quadrant 2. Okay, make sure you have everything labeled. Make sure you don't screw up as many times as I did, which is the nice part about using pencil. So after how many years will his car value equal the amount he paid to date for this car? So you can say during the 3rd year. If they said specifically, you could say 3.3 years. It depends on what the directions are. So describe the situation pictured above after 4 years. So after 4 years, your what you've paid for the car, so E of X is greater than D of X. So what you've paid for a car is greater than what it's worth. Okay. All right, let's try number 5. A car exponentially depreciates at a rate of 6% per year. Beth purchased a 5-year-old car for $18,000. What was the original price of the car when it was new? So we are going to use this formula over here. What was the original price? So that's what we're looking for. A. Y is the current value, so that is 18,000, over B, which is your base, raised to the T, which is the time in years. B is not here because B is 1 minus R, so don't forget that part. So our base is 1 minus our rate, so 1 minus 6% raised to our T, and our time is 5. So go ahead and put that in the calculator. So your A value is $24,526.37. So again, remember, it's money, so 2 decimal places. Go ahead and pause the video and you try the check for understanding. Continue to check your work. So this one you had to be really careful of the time because it only said 9 months. And remember, your time is in years, so that's why we had to do 9 divided by 12. Okay? And remember, it's money, so go 2 decimal places. Alright, another formula in example 6. Lee and Josh bought a used car for $20,000. When the car was new, it was sold for $24,000. If the car depreciates exponentially at a rate of $8,000 per year, approximately how old is the car? So X equals ln. We need Y over A. Y is your depreciated value of the car, and A is the original price. So we have 20,000 over 24,000 all over ln of 1 minus our rate, which was 8% a year. So go ahead and put that in. So we get X to equal 2.186, blah, 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 blah. So we can say during the second year, or the car is in its second year of existence, or something like that. The car is about 2 years old, something like that. Approximately 2 years old, okay? I guess I like that. I like that better. Approximately 2 years old. But make sure you have this part there, and then you write your little answer, okay? Don't just have your equation or your expression and then write the answer. Make sure you have the decimal there also, all right? Because it might say to round or something else. So how old would the car in example 4 be had it been purchased at half its value? So in example 4, the car originally was $26,600. So we're going to say X equals ln. The original was $26,600, so half of that is $13,300 over ln, 1 minus, and our rate in that one is 5.5%. So we're going to put that in the calculator, so go ahead and pause. And you should get 12.2528. So approximately 12 years old is when it will reach its half its value, which is a little bit weird for a car. Alright, if you have any questions, don't hesitate to ask. Good luck!